introduction. So I'm a fifth year PhD student here at Berkeley, and this is some work that I did about a year ago. But I think this whole idea of issue of adversarial examples is really something that's been coming to light over the last few years. So first, just to start off with, we should acknowledge that deep learning works really well, and it's what drives a lot of the consumer products that we consider to be intelligent. So we have things like facial recognition and translation and speech recognition. Basically, what's behind all that is deep learning. And when we say deep learning, as you probably know, what we're really talking about is neural networks. And so if we take object recognition as an example, neural networks are very good at recognizing objects and images, pretty much as good as people are. And this is really important for a lot of real-world applications. If you take robots or like anything that needs to interact with the real world, you need to be able to recognize what objects you're interacting with. If you're a self-driving car, you need to be able to recognize pedestrians or like what gestures they're making. You need to be able to recognize other cars and road signs and all of that. The problem is that back in 2014, Christian Zaghetti and a few of his colleagues discovered that actually neural networks work really well, but it's also really easy to fool them. And so they found that for a lot of images, so here we have this input image on the left. For a lot of images, you can compute this small worst case perturbation that you can then add to the image to create this new adversarial example, which to us humans looks pretty much exactly the same. That's still clearly a school bus. But when you feed that into this neural network, it thinks it's something completely different and wrong. And so this is the problem, because if we're a passenger in a self-driving car and it's driving along and it encounters a stop sign that's been adjusted just slightly that we as a passenger can't see, maybe it thinks that stop sign is a speed limit sign instead. And we wouldn't be able to detect that far enough ahead of time maybe to do something. And so this is a pretty big issue already, but actually something that makes it even worse is that, so here we had assumed that we had this neural network, we're calling it A, trained on some data. And here we assume that the attacker actually has full access to the internal workings of this neural network, and it can use that and the input image to construct this worst case perturbation to add on to it. But it also turns out that adversarial examples are transferable, which means that even if you have this other neural network B that you keep completely secret, and you don't let the attacker see how what the internal workings, what the weights of this neural network are, the attacker can still train its own neural network A on a different but similar data set of examples, and then use that to attack B, and it'll still be pretty effective. Not nearly as effective as if it were attacking A directly, but also effective. And so this is called transferability, because you're transferring perturbation from one network to another. And this even works if B isn't a neural network and if it's some other kind of model like a decision tree. It doesn't work quite as well, but it still works. And so this is a pretty big deal. There's been actually some more recent results that look at this in the real world. So if you can imagine a self-driving car, it's actually viewing the world from a lot of different angles as it's driving forward. So for example, if you're approaching the stop sign, you're seeing the stop sign from like a continuous number of rotations, and possibly different lighting conditions as well. But actually what this work discovered, and part of this was from UC Berkeley as well, is that you can basically construct these perturbations. They can either be these more, they call this a subtle perturbation. They essentially printed out a poster of a stop sign, and then that was the shape of a stop sign, cut it out, and then paste it on top of a real stop sign. And so this is a case where it just sort of looks like shadows on top of the stop sign. It doesn't really look like it's been tampered with necessarily, but that's able to confuse the network 100% of the time as this car is approaching and trying to classify this. It actually classifies it as a speed limit sign instead of
100% of the time.
Yeah. And so this was in the white. So we talked about white box and black box scenario. So this was in the white box scenario. They did assume full access to the network. So I think if they had been the black box scenario instead, I would be surprised if it were 100%. It'd probably be closer to maybe like 50 or something. Yeah, or you can do these more obvious but easier things that don't require printing out an entire stop sign. You can just add some stickers in very strategic locations and still manage to fool the network some amount of time with that. Yeah. So all of these examples I've talked about so far have been in this domain of supervised learning. And so in supervised learning, you basically, you have a particular input and you want to train the model so that it predicts the right output given that input. And so this is very, very broad. It includes a lot of application areas. Object recognition, which we already talked about, translation, also speech recognition, that all falls under supervised learning. And so what the work that I was doing was looking at is reinforcement learning. So the thing about supervised learning is that every input-output pair is independent from all the others. And so say you predict the wrong output on a given input, that doesn't affect your predictions in the future. You still sort of see the same distribution of inputs and outputs. But in reinforcement learning, you have this agent that's interacting with this environment. And so the actions that it picks is going to affect how the environment progresses, how the states of the environment progress, and what states it's going to see in the future. And so, for example, you can imagine an agent trying to navigate a maze. If it turns into a dead end, then it's going to make it a lot harder for it to continue navigating and exit the maze. And so in reinforcement learning, our goal is we have some sort of objective or reward function that we're trying to optimize. So something like you probably saw the really impressive results on Atari games a couple of years ago. That was using reinforcement learning, where the reward is just the score that you achieve in the game, like your number of points won in Pong. And you're trying to train an agent that learns how to optimize that, but is only receiving reward as its signal. So reinforcement learning is very similar to operant conditioning in psychology, where you get rewards or punishments and you learn to only do the actions that lead you to good consequences. And so what we were looking at specifically was deep reinforcement learning, where you parameterize your policy with the neural network. And so here, it's the same idea where you have an input to the neural network. In this case, it's a raw image observation of your state. And you map that to a particular output, and you learn this mapping between the input and the output. And so here, your output is just some sort of action on your joystick. And so neural network policies have been very successful over the past few years. People have gotten them to do things like reach human or above human level performance in Atari games, do really complicated robotic manipulation tasks, work on locomotion problems, and actually drive in the real world as well. And so I'm going to talk a little bit more now about actually how to even come up with this worst case perturbation in the first place that we've been talking about. And so it gets a little bit heavy on the math here, but I'll try and make it as intuitive as possible. So essentially, when you're creating an adversarial example, the adversary is finding this optimal perturbation data that it's going to add on to your input x. And that creates your adversarial example x, which looks the same to humans, but is able to fool the neural network. And so basically, the goal of the adversary is just to pick some perturbation data that somehow makes the network causes the network to make more mistakes, that maximizes this particular loss function J. And so one particular way of doing this is called the fast gradient sign method. And it's one of the most common ways of doing this because it's very simple but also very effective. And what this does is you assume this linear approximation for your loss function around your input x. So like the school bus image that we saw earlier. And then because you assume this linear approximation, there's a closed form solution for the optimal eta, the optimal perturbation, given that assumption. And so if you are trying to minimize the L infinity norm of eta, which in the case of image inputs would be you're only allowing the adversary to change a particular pixel by a certain amount, so that makes it harder for humans to perceive this adjustment, this perturbation. And so then it turns out that the optimal thing to do is just take the sign of the gradient of your loss function at that input, and then multiply by epsilon, and that's your optimal perturbation. So it's extremely easy to compute a perturbation given this example, these assumptions. And when this method, FGSM, first came out, people showed that it could reliably fool image classifiers, no matter how you're training them on what kind of data. And so the example that they showed in their paper was you take this image of a panda, the neural network is able to classify it correctly as a panda, and then you can compute this tiny, tiny perturbation. So that like 0.007 that's multiplied by it means that actually the image on the left and the right is exactly the same in terms when you discretize it into 8-bit image encodings. So when you're seeing it on the screen, they're actually exactly the same. You can't tell the difference. But a neural network is going to think that's a given if you just pass in the floats. So that was for object recognition, that example. And the way the loss function looks like for something like object recognition is you're trying to maximize the cross-entropy of the model's actual output and the true output, given your perturbation. And so if you have this panda here, the model actually outputs this distribution over possible classes for this image. And if you're the adversary, you're trying to get it to predict something that's not a panda. You're trying to minimize that probability and computing a perturbation that minimizes that probability. And so in our work for our policies, we do something that's similar. So a policy, a neural network policy, pi sub theta, is also going to output some distribution over actions. And in our work, the adversary just tries to minimize the probability of the most likely action. This is a little bit different than the supervised learning object recognition case, because here we actually have a y, which is the true correct output. But for this, in the case of policies, we actually don't know for a given state what the exact correct action is, because we just want this policy to optimize for reward. So there's not actually a true correct action that we know of in a given state. Like even if you take a really good human player for Atari, they're not exactly going to be able to label every state with the best action. And so we're assuming that the policy is already good enough such that the action that the policy already places the highest probability on is actually the correct action. So as long as we make the policy choose a different action, given the perturbation, it's going to do something wrong. And that's a pretty big assumption, but I'll show you some videos that show that that actually does decrease policy performance by quite a bit. Something else that we do in this work is we look at some different ways of constraining the perturbation. So in particular, I think the L1 norm is especially interesting in terms of constraining sparsity, because if you remember the image of the stop sign with the stickers stuck on it, that was a very sparse perturbation, pretty sparse, because you're changing a few pixels in the scene by a large amount, instead of changing every pixel by a tiny amount, which is what the L infinity norm does. And so this slide is basically just saying that even if you use these different constraints and apply FGSM, you still get these closed form solutions for the optimal perturbation that are really easy to calculate. And so here are some actual examples on Atari games. Pong has pretty intuitive adversarial perturbations. So here on the left, there's the actual state of the game, non-perturbed. And so there's a ball that's heading towards the paddle on the right, and the action that the policy chooses to take is up, which is correct, to hit the ball back. But if you let the adversary make a sparse perturbation, actually the optimal thing to do, and it's learned this by just taking a gradient on the policy, is to add in this fake ball that's a little bit underneath where the real ball is. You can see it more clearly on the right image. And that tricks the policy into moving down instead. And so this is a pretty obvious perturbation, since we optimize for sparsity instead of a very subtle perturbation. Instead, we can look at a perturbation that is more subtle, and like with the panda, the right image and the left image here are exactly the same in 8-bit image encodings. And still it's able to trick the policy into moving the paddle in the wrong direction and missing the point. And this is the policy that's been trained to basically win all points of Pong very easily, basically get to 21 points without losing a single one. And so we looked at how adversarial examples affect agents that we train with reinforcement learning using a few different algorithms. These are the state-of-the-art A3C, TRQ, DQN, and on 4 different Atari games. And essentially across the board, adversarial examples are quite effective, especially ones where we get to where we constrain the L1 norm, so where we get to perturb a very small number of pixels by large amounts. That's the blue curve here. And so the y-axis is the score of the policy, so higher is better. The x-axis is the level of the perturbation. So farther right means a larger, more obvious perturbation. And so you can see with the blue curve, it drops pretty steeply across all algorithms and all the games. So if you do allow the adversary to perturb even 1 or 2 pixels by a large amount, then that's often enough to completely prevent the policy from playing the game anymore. The dotted line here is where the L infinity norm perturbations become visible in terms of 8-bit image encoding space. And one other interesting fact is that there does seem to be a little bit of a difference depending on how you train your policy in terms of how effective your adversarial perturbations are. So in particular, DQN seems to be, policies that are trained with DQN seem to be least robust in terms of resisting adversarial perturbations. Yeah, so this is, let's see, this is for Pong. So these are with L2 norm constraints. You can see the perturbations in the middle there. Essentially, it's trying to perturb where the paddle is actually located and trying to confuse the policy that way. And so it's kind of cut off, but if you're a human player, you'd still be able to play this game. But as a neural network policy, it actually ends up losing quite a few points. This is what the policy how the policy would play if there are no perturbations at all. And on the right is with the perturbations added in. And we can see something similar with Space Invaders. Here, again, we're looking at L infinity norm perturbations. And so this image in the middle and that rightmost image, they're exactly the same in 8-bit image encoding space. So we can't tell the difference at all. But you'll notice that here the policy has no trouble shooting pretty much all the enemies, and there it just consistently keeps dying. And so one thing that we were especially interested in is whether adversarial examples are still transferable when your policies are trained with deep reinforcement learning. So the reason why they might not be transferable is that when you say you're training one policy with A3C and another policy with TRQ, like the attacker is trying to attack a target policy that's trained with A3C, and it doesn't know it's been trained with A3C, so it picks up some other algorithm to train its own policy and then compute out adversarial examples based on that to then attack the target policy. And so you wouldn't necessarily assume that that would work well, because when you're training a policy, like we talked about earlier about reinforcement learning, the actions that the policy takes is going to impact what states of environment it encounters. So if you train a policy with different algorithms, they actually might end up learning different strategies for the game, depending on how they explore the game. Or they might end up just learning different high-level features for the game. And so a perturbation that causes one policy to fail might not cause another policy to. So what we found is that is true. The red curve shows transfer across algorithms. If you train policies with different algorithms, the adversarial examples aren't extremely transferable, except in the case of L1 norm, that still seems to be quite transferable when you're allowed to change a few pixels at a time. The blue curve is when you're training with the same algorithm, just starting with a different random initialization of the policy. And so that also leads to different policies in the end. But transfer across that is slightly better than if you had to transfer across algorithms. And one thing, so actually we saw something pretty interesting in chopper command for this black box case. So in chopper command, you have this small map at the bottom that lets you see a pretty wide range of the game, and you can see where enemies are and where you are in the whole map of the game. And so what we saw is that when we let the adversary change only 1 or 2 pixels maximum in the game, it actually usually, you can see in this screen with the perturbations, it usually chooses to add little like fake enemies in that mini map of the game. And so this is, all we're doing is just applying FGSM, that standard method. And one thing this does tell us is that the policy is paying attention to the mini map, and that even across training algorithms, this can fool this policy. One other thing that I looked at more recently is this idea of dormant adversarial examples. You can think of this it's sort of comparable to brainwashing in a sense. The examples that I just showed were, at every time step we have a perturbation and we basically just want the policy to choose the wrong action at that time step. But with a dormant adversarial example, we basically, when we introduce the perturbation at time step t, we actually want the policy to keep doing the right thing for a while and then fail some time in the future. And so the idea behind this is that it makes it a lot harder to detect, because if you're in the case of the middle row, as soon as you see the policy acting improperly, you can just stop it there or take over control as an observer. But with the dormant adversary, you might watch the policy for a while and then trust it and think that, okay, well, this policy is doing the right thing, go do something else, and then the policy ends up failing. And so we looked at this in a pretty simple scenario to start with. There's this simulator called VizDo, where you're basically in a maze, and we constructed this iMaze here, where you start at this start state, and you see the color of the indicator. This indicator can be green or it can be yellow. And depending on the color of the indicator, you either go to the red goal or you go to the blue goal. And so this is with the recurrent policy, which essentially just means a policy with some sort of memory. So the policy remembers that the indicator is, say, green, and then realizes that it needs to go to the blue square. And what we found is that while the policy is going down the hallway, so here, this is a top-down view, what the policy actually sees is the actual view of within the maze. And so at this point, when the policy is just starting to head down the hallway, you can introduce this adversarial perturbation that's pretty small. I mean, you can see a little bit of a difference between this and this. But yeah, this is a pretty small perturbation, and you can essentially replace the memory of the policy with, you can get trick the policy into thinking that it had seen the yellow indicator instead of the green indicator, and get it to actually go to the wrong goal. So one option here, this is actually a little bit tricky because depending on how you perturb it, it's pretty easy to get the policy to just like turn around or start turning around endlessly or just do something incredibly, like very obviously wrong. But it's a little bit trickier to get it to actually do the right thing and go all the way down the hallway and then end up turning the wrong direction when it gets to the end. And the idea behind this is basically, instead of it's actually pretty straightforward, so we can still apply FGSM, but we have a more complicated loss function J. So instead of just trying to get the policy to fail at the current time step, you add a few more terms to this loss function and say, well, I want the policy to do the same thing for the next, let's say, 4 time steps, and then do the wrong thing at the 5th time step. And then you get something like this. So it's still pretty straightforward, very easy to do. Yeah, so a few takeaways from this talk. Adversarial examples, they're pretty cheap, they're pretty easy to compute, especially if you have access to the model of the neural network that you're trying to attack. This also doesn't just apply to neural networks, it also applies to other kinds of models like decision trees, like we talked about earlier, or even FCMs. But I think with neural networks, there are certain qualities of neural networks that make it a little bit more problematic. So the reason that FGSM works really well for neural networks, even though it's making this very simple approximation, a linear approximation of the loss function, it's because it seems that neural networks are learn these piecewise linear functions, and so they actually end up extrapolating quite a bit when you move far away from your space of possible inputs. And that's what you're doing when you're introducing this adversarial perturbation. You're moving away from this, like, you can think of a manifold of possible images, and by introducing a perturbation, you're moving a little bit away from that manifold. And because your neural net is extrapolating linearly, that means it ends up predicting something very wrong for that new input. So adversarial examples, they're transferable. So it doesn't really help even if you keep the weights of your neural network a secret. It's still possible for an adversary to attack that model. They exist across many domains. So I only showed examples for object recognition and our work on deep RL policies, but they've also been shown to exist for speech recognition and for spam detection. There was this interesting paper recently from Berkeley where you can take just a normal string of words, like a recording of words, add a little bit of imperceptible noise, and get it to say something like, okay, Google, navigate to like some spam website. And they exist in the real world as well with the soft science. That's especially recent work. There was also a recent work where there was an image of a turtle, or they took a picture of a turtle, and they took a picture of a turtle with a small, I think it was some sort of a sticker or something next to the turtle. And so with the original image, the neural network can very easily recognize it's a turtle. But with the new image, it thinks it's a rifle instead of a turtle.
It's a rifle.
Yeah, and this is what I would call a physical adversarial example, or that's the term for it, where you're actually doing the perturbation in the real world. The stuff that I was doing was you're just changing the input right before it goes into the policy. And so that does require access to adjusting your inputs. I think it's much more scary when you can actually do it in the real world. And so there's been, over the last couple of years, there's been a lot of work on adversarial examples, attacks, and defenses. And it's sort of been this cat and mouse game where there are some defenses proposed and then more attacks that override those defenses and then more defenses, and it just sort of keeps going back and forth. And it's not a resolved problem yet. But I think it's, I don't know if it's possible to come up with a defense that works against all adversarial examples, because there are, like, I only talked about 3 different kinds, the L1, L2, L infinity norm, but even those cover a really wide range of possible perturbations that you could introduce to an image. And it seems hard to be able to defend against all of them at once with a single model. Maybe you need an ensemble of models, maybe you need some sophisticated ways of detecting all different kinds of defenses, but I think it's more complicated than just finding a new training procedure, for example. So